Okay, hello everybody, this is Mr. Steele, and I'm here today to test this process out with pre-cal material. So what I've been doing the last week or so is I've been trying to create videos for the standard quizzes for Algebra 1, and I've had some success with that, and there have been a lot of kids that have kind of responded to that. So I figured I'd try this out with something that we're going to be covering in Friday in class, graphing a sine curve. And again, it's really going to be more a dress rehearsal for me for teaching it again for the first time in 2 years. But hopefully by posting this video, if it's any good, you'll have an extra resource to help you with starting out chapter or section 4.5 and 4.6 and all those other ones on a good foot. So to start off with, I'm not going to kind of derive it from the beginning like I will in class. What I'm going to kind of produce is just kind of the general ideas of the Graphing Manifesto, which unless there's an earthquake tomorrow, I will have kind of presented to you, or started off presenting to you, and then I'll actually do 1 or 2 examples of each one. So to start off, just to kind of get us going on here, the Graphing Manifesto is just kind of a list of pieces that we need to take care of when we're going through and graphing a sine curve. So the first one here, the shape, means that we've got to think about what this particular shape is actually going to look like and where this shape is going to fall on the actual axes. So it's kind of a motivation. What I'm just going to kind of show you is I'm just going to use my graphing calculator here. It's a TI-86, so there's one on there. So what I'm going to do is, assuming that I can actually do this, I'm going to go up here and I'm going to graph it. Shoot, it takes me a little bit to get used to this handle. Okay, so I want to graph sine of x and just see what it's like. In class we'll actually have gone through all this stuff and kind of shown it on the calculator. So here's sine of x to give us an idea about the shape. I'll hit graph. And notice, get these little bounces. So it's going up and going down, up and down. It's kind of wavy. In fact, sines model waves. If you get into that kind of physics, it's pretty cool. But basically that's our shape. We've got kind of these bumps. Now, if we were to graph cosine, we'd see that it's a similar kind of shape. The important piece for sine is that in the center here, right about there, where my shadow is, right there, it goes through the origin. And so we're always going to start graphing our sine curves like that, by starting at the origin and then going up and down. So first off, like if we're talking about this Graphing Manifesto, when we talk about the shape, we know that a sine looks like this. So it starts at the origin, goes up, comes back down, and then it goes, continues smoothly the other side. Now it's not perfect, obviously it's a little scrunched together. That's not so much, that's okay. Okay, so for sine, it's through the origin. Okay, well, unfortunately, that's our shape, but number 2 talks about reflection, so we've got to look and see if it's maybe a negative sign, what would happen. So to kind of simplify this, so that's a positive sign. It's still always going to go through the origin, that's always true. But when we think about reflection, if we happen to have a negative sign, we're going to have to just reverse that setup. So instead of starting at the origin and going up, we'll just start at the origin and go down. Same shape, still up and down, still those little humps, little bumps. And there we go. That'd be a negative sine curve, still through the origin. Okay, well once we get to there, on Monday we'll actually talk about 3 and 4, the phase shift and vertical shift, because I have some nifty little tricks that another teacher showed me for making that part easier, because it's sometimes kind of tough to move these guys around, side to side or up and down. But number 5, talking about the period, is actually a pretty important piece. Like in order to actually graph this thing and say that we have the right sine curve, we've got to label some of these boundaries, like the points at the end, or one period, or one full loop-de-loop of the function ends, as well as the other side, and then probably a half one just to make sure everything's in there. So to find the period for a sine curve, if we're looking at a general one like this, y equals a times sine of bx, you'll find the period by taking 2 pi and dividing by that number b, whatever number that is. So again, the reason we do that is because a full period of sine is 2 pi, and if you think about that, that should make sense, because 2 pi radians is the same thing as 360 degrees. So if you go all the way around the circle, well then you get back to the same kinds of angles. They just, they've just gone around the circle more, so they'll have the same sine, cosine, etc. They'll just be, bigger angle measures that we're looking at. So we'll find the period this way, and then what we'll do is we'll take that and we'll actually label the extremes. Like we'll go to one side and we'll label this as 2 pi over b, whatever that is, because there's no phase shift. We'll worry about that later. And then on this side we'll go to negative 2 pi over b, just to kind of get us started. Lastly, the amplitude is going to be the absolute value of the number in front, so that a times sine theta, the amplitude will be the absolute value of a, and that's just going to be the different, or half the difference between the highest and lowest points on your sine curve. For traditional one, for just regular sine of x, the amplitude is 1, so that means up to the top is 1, all the way down to the bottom is negative 1, so half the distance would be just 1. Okay, so there's kind of the background. So now let's actually look at a sine curve and let's graph it using these kinds of strategies. Show you what it actually looks like in context. Okay, now that an example has magically appeared right here, I'm going to go ahead and try and actually show you how to graph this sine curve. And first of all, while I'm sitting here thinking about it, I absolutely cannot stand my voice on these videos, and if anyone knows how to modulate it down, not necessarily as low as Darth Vader's voice, but maybe maybe a couple whole steps above that, that'd be great. Just let me know. I'd love to have my voice sound a little bit lower on these things, because right now I feel like I'm channeling one of those old paint by the numbers guys on PBS. So, as far as graphing this guy, so we want to graph this sine curve. Again, we could look in the calculator and cheat and just kind of draw it up there, but that wouldn't be good, and that wouldn't help us on an actual test, would it? So, to start off with, we want to actually graph this, so using the Graphing Manifesto, we've got to start and think about the shape first. So, if we're thinking shape, our sine curves always go through the origin. So it's going to go through the origin and go like this, or if it's negative, it'll go like this. Did I do that right? Okay. So we've got the shape. It's going to go through the origin, so that'll be good. In fact, I can kind of label that point right now. Just say, okay, there's my origin. But now we have to look at reflection. So if it's a negative sine function, it's going to be reflected downward. So looking at our equation, I think you can see right there that in fact it is a negative sine function. It's negative 3 sine of 3x. So in fact we're not going to go origin and up, we're going to go origin and down. So let me go ahead and try to do that. And again, I'm using multiple colors here. I have no idea if they're actually showing up on the video because I don't really see it very well. Okay, so I'm just going to put some dots there. Then again, I'll go back. Okay, that's going to annoy me, so let me fix that. There we go. Totally perfect. Okay, and there's my start of my sine curve. So I've got the shape and reflection done. The artistry of the Graphing Manifesto is taken care of. Okay, now on to labelry. So again, we're going to ignore phase shift and vertical shift for now, and that's actually smart because there is no phase shift and there is no vertical shift in this particular problem. That's why I chose it. And now let's look at the period. So we've got to actually find the period in this case before we can start labeling things. So to find my period, we're going to take 2 pi, the period of a normal sine function, divided by b, whatever's in front of the x. In this case, what's in front is a 3. So we can divide 2 pi by 3, and that's going to be my period. So when I go to mark this on the actual graph, I'm going to use a darker green pen. You probably can't tell the difference. I'm going to go from here first. So here's my starting point. This is x equals 0. Now I'm going to go over to the extremes, the end of one period. Since notice it starts at the center, goes down, comes back up, and ends the center again. So that's one full period. I'm going to label that 2 pi over 3. Okay? And now on the other side, since we want to go back one period, it'll still be one period away when it finishes this loop. So this will be negative 2 pi over 3. Okay? This should make sense. That's just showing one period. Again, we want to get that full motion, that normal sine motion where it starts at the origin, then goes up or down, follows that loop. And now if we want to be really careful and make sure we're really plotting this a little bit better, we should also label the half period. So halfway between 0 and 2 pi over 3 is going to be 1 pi over 3. So I'm going to label that here. And I'm going to label it over here. And now just because it's hitting me, you might wonder, well, that's kind of interesting. It looks like we're labeling the 0 right there at pi over 3. Would pi over 3 be a 0? And the fact is, if we plugged in pi over 3 here, we'd have y equals negative 3 sine of 3 times pi over 3. Well, those guys would make a 1. We'd have negative 3 sine of pi. And the sine of pi, if you remember, the coordinates of pi are negative 1, 0. So our sine is our y value. So this would be equal to 0. So in fact, pi over 3 does happen to be a 0 in this case, which is kind of cool. Although you're probably just thinking, why the heck did Mr. Steele just go off on that tangent? Well, it's because it hit me and it inspired me. Sue me. Okay, so there we go. We've labeled stuff. Now we've just got to take care of the amplitude. And again, amplitude's in the label section of the Graphing Manifesto because it really comes down to just labeling stuff. So first, let's technically find it. I know this will be one of those things that eventually you'll get kind of quick at, but for now, let's be careful. So the amplitude is the absolute value of whatever number's in front. In this case, that number that's multiplied times sine is negative 3, so the absolute value is positive 3. So what that means is that's going to change how high up and how low down our peaks and valleys are going to become on this graph. So first, just kind of keep it straight. This is y equals 0. There's no vertical shift. And again, if you wonder why I'm doing stupid things like that, the reason why is because I'm trying to set you up for when we actually do phase shifts and vertical shifts. Ignore that again if you don't want to listen to it. And now when we actually go to label it, we just want to label how high and low those points are. So the amplitude is 3, so this is 0, so the distance up here, this is going to be positive 3 up. And then the low point is going to be negative 3. And in fact, according to my Graphing Manifesto, we done. So the question is, are we close? Like, did we actually make this look right? Like, is this anything like the actual function? Well, I don't know. If only we had some sort of tool in which we could, check to see if something's graphed. Oh, wait, we do. We have graphing calculators. So, this thing is kind of annoying, but I'll do my best to try and do it on here. So first I'm going to punch in the equation. So, negative 3 times sine of 3x. Okay, so you might notice mine doesn't actually provide parentheses automatically for you, so it's kind of annoying, but that's okay. Okay, so here's our function. Hoping the little camera autofocuses. Okay, now I want to make sure my window looks exactly the same. So if we look at our picture here, when I go to look at my window, I'm going to go from negative 2 pi over 3 to 2 pi over 3, because those are the boundaries we put it at, 1 period each way. So notice you can't see the top one's a decimal approximation of it, the second one's there. For the scale, who really cares right now? I'm not going to worry about the scale for the moment. For the max and min, well, we got to go from negative 3 to 3 at least, so I'll give myself a little bit of room here. I'll go from negative 4 to 4 with a scale of 1. There, that looked good. Okay, so there we go. So now we've got the exact setup we have here. Let's see how similar our picture looks. I'm getting excited. Are you getting excited? I'm getting excited. But look at this. They're like twins. Look at that. Mine's more colorful. Look at that. Tell me that's not awesome. That looks like a pretty close approximation of what we had there. Yeah, we did that. Nice. Okay, well, that's fun. I'm getting a little goofy here because it's getting late, but I'm going to do one more just to kind of get that in your head, make it a little tougher. Okay, give me just 1 second.